Hello. In this final video in our unit on states of matter, I'm going to talk about one final topic related to Chapter 10.4 on changes of state and talk briefly about the special properties of water and where they come from. So let's begin. So imagine an experiment in which you take some sample of matter, it could be an element or compound, it doesn't matter, and simultaneously change the temperature and pressure of that particular state of matter. So vary the temperature it exists at and vary the pressure exerted on it. And then measure and graph the physical state or phase that it exists in that particular temperature and pressure. That is, whether it's a solid, liquid, or gas at every given temperature and pressure. Now, this is an unusual experiment because unlike most experiments that have an independent variable and a dependent variable, this actually has two independent variables. Because we are changing the temperature and pressure simultaneously, they're both the independent variable, whereas the outcome, that is, the physical state in which the substance exists at that temperature and pressure, is the dependent variable. Well, this is what a depiction of the results would look like. And as you can see, it's a two-dimensional Cartesian coordinate system, but we have both of the independent variables, both temperature and pressure, on the axes. It kind of doesn't matter which axis we put which variable on, but by convention, we put temperature on the horizontal axis and pressure on the vertical axis, and then on the graph, we indicate whether at that particular point the substance is a solid, liquid, or gas. This type of diagram is called a phase diagram. A phase diagram shows the phase or physical state in which the substance exists at that given temperature and pressure. Now, because there are three physical states we're dealing with, there will be boundary lines that separate the physical states. And these boundary lines indicate all of the temperature and pressure points at which two phases, that is, the two phases on either side of the boundary line, are in equilibrium with one another. And a phase change occurs, that is melting or freezing or whatever, when you cross a boundary line from one phase into another. There is a point on all phase diagrams in which all three physical states are present in equilibrium at the same time, and that point is called the triple point. There is also a really interesting point called the critical point, and as I'll talk about in a second, if you heat the sample to a sufficiently high temperature but keep the pressure high enough, you will actually reach a new physical state where the distinction between a gas and a liquid disappears, and you have what is called a supercritical fluid. So any temperature higher than the critical point, or I should say any temperature and pressure higher than the critical point, will result in a supercritical fluid. I will show you in class a video that actually demonstrates this. The normal melting point is defined as the temperature at which the solid and liquid are in equilibrium at 1 atmosphere pressure. Normal indicates 1 atmosphere, which is a special pressure. And likewise, the normal boiling point is the temperature at which the liquid and gas are in equilibrium at 1 atmosphere pressure. Now, here's what I expect you to be able to do if I give you a blank phase diagram. Number one, label the regions of the phase diagram. That is, indicate clearly which region corresponds to a solid, which region corresponds to a liquid, and which region corresponds to the gas phase. If I specify a particular temperature and pressure, you should be able to find that point on the graph, and then based on which region it lands in, tell me which phase or physical state is present at that particular temperature and pressure. You should be able to identify clearly the triple point, the critical point, the normal melting and boiling points, and you should be able to name the phase change that will take place when one of the two variables is held constant and the other increases or decreases. So for example, if I say let's hold the pressure constant at a certain value and increase the temperature from one temperature to another, tell me which phase change will occur. So here's an example of a phase diagram, and as you can see, it's got pressure on the vertical axis and temperature on the horizontal axis, and it has boundary lines. Now, let me point out that I completely fabricated this phase diagram. This does not correspond to any real material. It is just for educational purposes. Now, one other interesting thing that you'll see if you look at the pressure axis, you'll see that although the pressure is labeled in atmospheres, it is by no means linear. It is not a linear scale, and that's okay. Sometimes we can have nonlinear scales because it helps us see things differently. So let's go through some sample questions that I expect you to be able to answer. So, number one, label the solid, liquid, and gas regions on the phase diagram. Well, I don't expect you to memorize these, but I expect you to figure it out. Suppose we are at very, very low temperature, so we cool it way down, and very, very high pressure. We press on it very hard. Well, obviously that's going to favor the solid phase, low temperature and high pressure, so we'll label this region generally as the solid region. In the other direction, imagine that we raise the temperature to a very high value and decrease the pressure. Well, that's going to cause the particles to separate out, and that will give us the gas phase. Then obviously the region in between must be the liquid phase. And it's always the case that it looks like that. Specify the temperature and pressure of the triple point and the critical point. Okay? Well, the triple point, as we said, is the temperature at which all three phases are present simultaneously in equilibrium. That must be the point where all the boundaries converge. So that purple dot represents the triple point, and that's obviously a temperature of 20 degrees Celsius and a pressure of 0.5 atmospheres. The critical point is the point where the distinction between liquid and gas disappears. So if you look at the boundary line between the liquid and gas phases and go to the maximum value that's recorded, which as we can see is, pardon me for a second, which we can see is way up here, that must be, oh, I forgot to label this, that's the triple point. That must be the critical point, and any temperature and pressure above the critical point corresponds to a supercritical fluid, which, as you'll see in class, is a fluid phase that has some properties of a liquid and some properties of a gas. Oh, and I forgot to record the temperature and pressure, so that would be 100 degrees Celsius and 10 atmospheres. Specify the normal melting and boiling points. Now, we said that the normal melting and boiling points are temperatures at which two phases are in equilibrium at a pressure of 1 atmosphere. So I'm going to record what 1 atmosphere looks like. So here is a line that represents 1 atmosphere, and the temperature at which the solid and liquid are in equilibrium, that is, where 1 atmosphere crosses the solid-liquid boundary, must be the normal melting point because solid and liquid are in equilibrium simultaneously. And correspondingly, the temperature at which the liquid and gas are in equilibrium, so the point where 1 atmosphere crosses the liquid-gas boundary line, must be the normal boiling point. So those would appear to be 40 degrees Celsius and 80 degrees Celsius. What phases are present at 20 degrees Celsius and 10 atmospheres? Well, I simply go back to the diagram and find a temperature of 20 degrees Celsius and a pressure of 10 atmospheres. It's right there. And I see that we are in the solid phase. What phases are present at a temperature of 90 degrees Celsius and a pressure of 5 atmospheres? Well, at 90 degrees Celsius and 5 atmospheres, oh look, I happen to land right on the liquid-gas boundary line. So what that means is that at that particular temperature and pressure, I have liquid and gas in equilibrium. What that means is that at a pressure of 5 atmospheres, the boiling point of the substance is 90 degrees Celsius. Let's see. Can this substance exist in the liquid phase at a pressure of 0.1 atmospheres? Why or why not? Well, if I go back to the phase diagram and look at a pressure of 0.1 atmospheres, I will see that we are below the triple point pressure, so that means only the solid and gas can exist, the liquid cannot exist. And that is generally the case. If you have a substance and you're at a pressure that is below the triple point pressure, you can only have the solid and gas phases. You cannot have the liquid phase. So for that I will say no, because 0.10 atmospheres is less than the triple point pressure. This, by the way, is the reason that dry ice, which is solid carbon dioxide, does not exist in the liquid form at atmospheric pressure. The triple point pressure of carbon dioxide is greater than 1 atmosphere. What phase change occurs when the pressure exerted on a sample of the substance at a constant temperature of 60 degrees is raised from 0.1 to 5 atmospheres? So I'm going to go to a temperature of 60 degrees and increase the pressure from 0.1 to 5. So here's 60 degrees. I'm going to go from 0.1 to 5 atmospheres. And as you can see, in that transition, we are crossing the gas to liquid boundary, which means we are going from the gas phase to the liquid phase. The name of that is, of course, condensation. What phase change occurs when the temperature of a sample of the substance at a constant pressure of 8 atmospheres is decreased from 80 degrees to 40 degrees? So we'll go to 8 atmospheres and go from 80 degrees Celsius to 40 degrees Celsius. 8 atmospheres is about right here. So when we go from 80 degrees Celsius to 40 degrees Celsius, we cross the liquid to solid boundary line, which means we're going from the liquid to the solid phase. And that, of course, going from the liquid to the solid is called freezing. So those are the sorts of things you should be able to do with a phase diagram. Now, on this slide, I'd like to show you the phase diagram for an actual physical substance, which is water. And it's kind of interesting. Found this on the internet. And as you can see, it looks like the phase diagram we saw before, the one that I made up. The difference would be that, well, first of all, we do have temperature on the horizontal axis and pressure on the vertical axis. And we can see, as I mentioned before, neither the temperature nor the pressure axis is linear at all, and that's perfectly okay. That helps us see differences more clearly. We see a triple point, we see a critical point, and we see a normal melting point and a normal boiling point. But do you notice anything qualitatively different about this phase diagram compared to the one I showed you before? Well, as you can see, this boundary line, the one that is between ice, the solid phase, and water, the liquid phase, has a negative slope. Instead of pointing in the forward direction, it's pointing in the reverse direction. So, what does that mean? Well, if the boundary line between the solid and liquid phases has a negative slope, what that means is that increasing pressure favors the liquid state. So, if let's say for example, I am at 0 degrees Celsius and I'm just below 1 atmosphere, and I increase the pressure while holding the temperature constant, notice what I do, I cross from the solid phase into the liquid phase, okay? Well, because the more dense phase must be the one that exists at a higher pressure, makes sense that if you increase the pressure on something, it's going to become denser. What that must mean is that the liquid phase is denser than the solid phase. And that's the case anytime your phase diagram looks like this. Anytime you have a negative slope between the solid and liquid phases, that means that the liquid phase is denser than the solid, which of course is why ice floats. You know that water is unusual in that the solid phase is less dense than the liquid phase, and that is a result, is explained by the fact that the boundary line between the solid and liquid phases has a negative slope. So why is that? Why, chemically, is the solid phase of water, that is ice, less dense than the liquid phase? Well, here are a couple of diagrams I found that actually clearly show this. On the left, we see liquid water, and we see the water molecules sort of rolling about and tumbling and free to move. They're not locked in any particular position. And we can see that even though the particles are free to move, there's still lots and lots of hydrogen bonding. There's a hydrogen bond, there's a hydrogen bond, there's a hydrogen bond, there's one, lots and lots of hydrogen bonds. But when we cool it down, when we remove heat energy, the water molecules start slowing down, and then suddenly they lock into a solid form in which there is very, very strong directional hydrogen bonding between adjacent water molecules. And that has the effect of locking the molecules into a rigid crystalline lattice. And as you can see, there's lots and lots of empty space between the molecules. Okay? So that means that when water freezes, it expands, making the volume increase and the density decrease, which is pretty cool. So let's finish up by summarizing some other properties of water that are explained by the fact that there is extremely strong hydrogen bonding between the molecules. As we talked about in our video on liquids, water has very, very high surface tension, again because the molecules are so strongly attracted to one another. Strong capillary action, which is related to the surface tension. Remember that the water creeps up a thin glass tube because it's very strongly attracted to the polar glass surface. Water has an unusually high boiling point. For such a small molecule, it's very unusual that water exists as a liquid at room temperature. Having a boiling point of 100 degrees Celsius is indicative of extremely strong hydrogen bonding, extremely strong intermolecular attractive forces, and water also has a relatively high enthalpy of fusion, meaning it takes a lot of heat energy to go from the solid to the liquid phase. And it also has a very high enthalpy of vaporization because you have to overcome those strong hydrogen bondings in the liquid phase to turn it from the liquid into the gas. Well, that pretty much concludes our section on properties of water as well as our unit on physical states of matter.